Okay, guys. Well, first, let me apologize for Friday's work, or I guess it was Thursday's work, saying how easy it was going to be. And then it actually ended up being kind of complex. I thought with the formulas being so easy that the work was going to be very simple too. But, I mean, in retrospect, the only thing that was really difficult about the last day's work was direction. And since direction is going to play a prominent part in today's stuff, you'll be used to it after today. I can a lot more confidently say today's work is going to be very easy work that you're going to understand very well. Okay, so all the questions on this next day of work are going to involve things colliding and what happens to speeds after objects collide together. There's all kinds of different scenarios. Sometimes objects collide and they bounce off of each other. Sometimes they collide and they kind of push each other. Sometimes they even link and join together into one mass after the collision. Today's work, conservation of linear momentum, is going to allow you to calculate what happens to speeds after collisions regardless of what happens. And the only thing that you need to know is this: the law of conservation of momentum. And you don't have to write this out every time, and I couldn't even fit it all across a page, so I used a ... But the law of conservation of momentum is very much like the law of conservation of energy that you used in grade 11. If you add up all the energy before something happens, it will always equal the energy at the end of a situation. And in grade 12, it's actually the same for the momentums. If you add up, if you take the sum of all of the momentums of every object before a collision, it will always equal the sum of all the momentums after the collision. And that will allow you to calculate for speeds. So all you need to do in this work, just like you did in grade 11, there's no particular formula. The only thing that you have to know for today's work actually is just this: momentum equals mv. That's it. But what you're going to do is you're going to write one of these little MVs for every single object that you find in a question. And you're going to build a left-hand side of a situation and equate it to the right-hand side of a situation. So let's try this first example, because really there's no notes on this. You just have to do it based on examples. So here's what you have in the first question. Just read through it. A 5 kilogram object is traveling 5 meters a second to the right, and it runs into a slower object, a 2 kilogram object traveling 3 meters a second to the right. And the question is, they join, that's important. They join together in this situation. What's the new speed and the new direction of the new object? So what you do is you write a left-hand side of this formula that has a momentum for each one of the objects. So there's a 5 kilogram object, we'll call that object 1. So there's the momentum of object 1, and we're going to add it together with the momentum of object 2, and that's it. There are 2 objects before the collision in this question. At the end of this question, the 2 objects collide and they join. So on the other side of this equation, there's going to be a single object with a single momentum. And we can call that object 1, 2 if you want. When I was in university, we most often just wrote the word total, like one total package. So understand this second line, because this second line is going to look different for every question. Exactly what it's showing. There's 2 objects with 2 totally separate momentums of their own in the beginning. They join together and become one object. That's it. If you understand that line, the rest of the question is just substituting in this result. P always equals mv. See, this is easier than this is easier than conservation of energy in grade 11, because you had 2 different energy formulas. Well, this time we're doing conservation of momentum, and it's always the same formula, mv. So it's even easier than grade 11. So we have an mv for this object, an mv for the next object, and an mv for the object in the end. And you got to be really careful, because these masses aren't the same. So you want to label the masses as different masses, M1, M2, and this one I'm just going to call MT because I can't fit that word in there anymore. And the speeds are also not the same speeds. So you want to label those lowercase v's as well so that they stand out as different from each other. And this is something that you have to get used to doing now that you're through grade 11. When you write a general formula, you always want to try and label as much as you can in the lower right-hand corner just to keep things organized for yourself. Okay, so the only thing that you're going to get wrong if you do something wrong on any of these momentum questions is you're going to forget that these V's have to have direction on them. It's always the sum of the momentums before equals the sum of the momentums after. And you do write nothing but positive signs in these formulas. Add them all up, add them all up. But when you go to your third line, when you go to do your substitutions of values, that's where you want to consider direction on the speeds. And you want to use plus and negative signs depending on which direction things are traveling. So let's do the substitutions here. The first mass is 5 kilograms. The first speed is 5 meters a second, but it says it's to the right. So I'm going to use a positive sign just because by standard, positive usually is used to indicate right and left is negative. Positive 5 meters a second. And that is going to collide with a second object. The mass of the second object is 2 kilograms. And the speed of the second object is given as 3 meters a second to the right. So I'm going to put a positive sign there. 3 meters a second. And they are going to join together. And we're going to solve for the speed of the new mass afterwards. Now you can't have two unknowns in one formula. So the total mass afterwards is obvious. These linked together, it's going to be a 7 kilogram mass. And that's not given, but I don't think I need to write any more details than that for a question that's this easy. 7 kilograms, and the speed in the end is VT, the speed of the total mass, with no sign on it because you don't want to be biased to say it's going to be forward or backward or whatever. Just let the math work itself out. You don't need another line of work because there's always just going to be one unknown. So you can isolate and you can solve for the only unknown. And if this question looks like it doesn't need the positive signs, because it certainly doesn't. If you didn't put these positive signs in, BEDMAS would still give you the same answer. But if one of these was negative, if one of these was to the left, and you forgot to put the signs in, you would get the question wrong. So my suggestion is always, 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 always put a sign in front of the speeds, even if you know exactly what the sign is and you know it's not going to mathematically make a difference, put it in anyway. And then just do your BEDMAS properly, and you don't have to show any other work other than this, and you'll get a final answer in the end, and the final answer will have a sign on it as well. This time it comes out to 4.43 meters per second, and there's no sign on my calculator, which indicates that it's plus. So it's a positive 4.43, and in my final answer I would write therefore 4.43 meters per second to the right as a final direction. They always want direction in the end. You wouldn't be able to predict that number by just looking at the numbers in the question. You have to do it mathematically. This first example is maybe a little bit of an easier example because both objects are moving forward. So obviously if a fast object runs into a slower object and they're both moving the same way, the new object is going to move the same way. But let's do something that's a little bit less intuitive. What if you have an example where you've got a really big, heavy football player traveling slow, and that football player runs head-on into a very fast football player who's very light? Who's going to win? In other words, who's going to push who back? You would not be able to predict that unless you went through the math. And so let's do this question. You can read this question first, and what you'll find is there are two runners in a head-on collision beforehand, and then afterwards one of the runners gets knocked backwards, and we want to find out what happens to the other runner. They don't link together. It clearly describes what happens. So my first line in this question is going to look like this. There's one object beforehand, there's another object beforehand. Totally different objects. Player 1 and player 2. And that's not a P for player, that's the momentum symbol. So two separate momentums in the beginning, And now here's the funny part. At the end of this question, there's two separate objects as well. They don't link together. Well, that's a bit of a problem because in grade 11, you were using little 1s and 2s in the lower right-hand corner for before and after. Remember, V1 was before, V2 was after. Sometimes in the textbooks, you don't see them using 1s and 2s, and the reason is because of this right here. When you get to university, sometimes 1 and 2 isn't good enough. I mean, if this is object 1 and this is object 2, and they're both at the beginning, in the end, we still have object 1 and object 2. Well, that's not good enough. Things would cancel, left-hand side, right-hand side. So you need a different way of labeling these things. You could call it 1B, 2B for before, or 1A, 2A, 1B, 2B, whatever you want. But you need to make them different. One way that you're going to see in September in university, and it's kind of a weird way, is they just put a little tick in the top right-hand corner. It's a prime sign. You've seen it in math class before. I don't know why they use a prime sign to indicate after. Like, to me, prime sounds like it means before. But you're going to see little prime ticks used quite a bit on variables that just indicate that that's a later version of the same variable after undergoing some kind of change. So I'm going to leave those prime signs on there. But that's it. If you understand that line describes exactly what happens. Two separate objects collide together, and there's two separate objects afterwards as well. Next, you need another general formula line. Remember, you have to show exactly what you are subbing into. You can't just start putting down masses and speeds without a second general formula that shows these variables that you are going to sub into. Okay, got those in there. Now it's time to do a substitution line showing all the numbers, and you want to put signs on every one of these speeds. I used to do this when I was in high school. Actually, when I was in university too, I would get ready to write all these things in the question with a long list of brackets before I even started, just to make sure I didn't forget everything. Each one of the speeds I want to have a sign on it though. So let's very carefully read what happens here. A 95 kilogram player, 95 kilograms, we'll call that mass 1. 95 kilograms is running at 1.5 meters a second. It doesn't say left or right, but you got to choose something. And this is the very first object and the very first speed. So I'm going to call that forward, and I'm just going to use a plus. I don't know whether it's left, right, north, south, east, west. My positive sign in this question is going to be forward. So anything that goes backward, I'm going to use a negative. See, that's the thing. It's not a sign convention where there's a certain way that you have to use plus and negative. It's for your own organization. Okay, 95 kilograms, running at 1.5 meters a second. The smaller player is 3 times that speed, and a 65 kilogram runner. Okay, so much lighter. And this is a head-on collision. That's a direction. So that means that the smaller player is running toward the bigger player. If the bigger player is positive 1.5, then the smaller player is negative. Completely different direction. The smaller player is running backwards. And 3 times that speed, so 4.5 meters per second. Okay, you can't solve these questions if you have too many unknowns, so we should be able to sub in at least 3 of these brackets over here on the right-hand side. You have to have one unknown to solve for. So what is it? Well, the 95 kilogram player is still 95 kilograms. There's no change of mass here. It says in the question, the smaller player is knocked backwards at 0.5 meters a second. Be really careful with this right here. What does that mean, knocked backwards? The small player is in a head-on collision, running in a backwards direction, or toward the larger player. Now the smaller player gets knocked backwards to the direction that they were traveling. So this is going to have a positive sign on it. Think of it like this. I don't have any room here. Big player, smaller player. Let's draw it like that. Big player is moving to the right with a positive direction. Smaller player is moving to the left with a negative direction. Now the smaller player is going to get knocked backwards, which is going to be a positive direction. So the smaller player is knocked backwards 0.5 meters a second, still 65 kilograms. And the only unknown in this question is V1 prime, the speed of object 1 after the collision. And notice how I'm not putting a sign on that speed. I'm not making it plus, not making it negative. We don't know. Actually, that's the whole point of this question. Which direction is it? Does the larger player get hit and actually knocked backwards, or does the smaller player just plow right through the little guy and keep on going? You would not be able to predict it until you run through this math. But you don't need another line of work. You can sub all this into a calculator. It's easy because there's no exponents, there's no square roots, anything like that. It's just straightforward, easy bed mass. Use lots of brackets. That's all I suggest, because you need to have you need to have the negative sign right there in there for sure, and any other signs that might affect the answer. So I'm just punching this in off to the side, and I hate talking while I'm doing it because I'm afraid I'll make a mistake. Okay, minus 65 times 0.5. So the answer to this question is 1.92 meters per second, and it's negative. So think about what that means. Not only did this small player hit the big player head on, but the small player creamed him. I mean, he knocked the big guy backwards faster than he was traveling in the beginning. He was traveling 1.5 meters a second. He gets knocked backwards 1.92 meters per second. So he got absolutely clobbered by this speed, and it's negative. So therefore, final speed, 1.92 meters per second, and they want a direction. I'm tempted to write left, but there was really no left in this question, so I'm going to write backward, or backwards. Easy question. If you saw these two solutions prior to going through this line by line, you'd be totally stressed out. But when you approach it line by line, systematically, it's really easy stuff. Normally I cut it off right there, but let's do one more example, because what you're going to see next year, the most common one-dimensional momentum questions are trains. They love to use trains because they can make every mass, every car on the train exactly the same, and make a question that's got some unknown variables, and they love to do that, of course. So here's the question. A train is comprised of 8 identical train cars. I'm actually going to draw that. So here's what we have in the beginning. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 cars. They don't even tell us the mass, but there's 8 of them. Let's make it X. Don't even know what the mass of this train car is, but they're all X. It's going down the track at 12 meters a second. And again, it doesn't say left or right. We'll just consider it a forward direction. A bomb has been placed inside the hitch between the 3rd and 4th car. 1, 2, 3, 4. So right here, right between these 2 cars, there's a small device that is going to explode and separate the train into 2 different pieces. So afterwards, we're going to have this. We're going to have 1, 2, 3, 4, 5, and 1, 2, 3. So the train is going to separate into 2 pieces, bigger and smaller. Now the question is, which way are these masses going to be traveling? It's not as easy as you think. Just because a bomb explodes between the 3rd and 4th car doesn't mean that the 3rd car will go further down the track and the big piece will go backwards. It could be enough to separate them and still have both masses rolling forward down the track. So that's the question. You really don't know. It does say in the question here, it says the smaller section of the train is blasted forwards, 30 meters a second, down the track. Here's the question though. Which way does this go? And if you think that it's obvious, it's not. Think about what could happen here. That explosion could be enough to actually push this mass to the left down the track, Or because the whole mass is moving in the beginning, maybe it's going to push that mass backwards but still be rolling forward. It's kind of a relativity question. Anyway, the point is, you don't need to guess. The math will do it for you. So here's our situation. We've got a total mass in the beginning. It's a one total momentum, and it's going to split into two. I could put little prime signs on it if I wanted to, but actually it's not even required in this question because nothing's the same left side, right side. So these three variables are already completely different. So a total mass in the beginning, one momentum, is going to equal two different objects in the end. And if we add up their momentums, they have to be the same as what it was in the beginning. Let's put in the variables. The total mass in the beginning multiplied by the total speed of that object is going to split and become m1 v1, m2 v2. Now it feels like there's not enough information given here, but this is why they always use trains with identical cars. It did say 8. So there's 8 identical cars in the beginning. So we don't know what the mass is, but there's 8 of them. There's 8 of these x masses. The speed in the beginning is 12 meters a second, but don't forget, put a sign on it. It's going forward 12 meters a second. It'll be really important in this question because we need to know the direction of that big mass afterwards. Okay, what happens afterwards? The smaller, let me do them in the reverse order just because of the way I drew them. The larger mass, this one here, 5x's, whatever that is traveling at a speed of v1. And we don't know whether it's plus or negative. This is the unknown. So traveling at a speed of v1. The smaller mass is 3 cars, 3 of these x cars. And it is definitely traveling forward 30 meters a second. So there it is. There's only one unknown in the question. Obviously there's an unknown x, but it's every single term on the left and right has it, so you can cancel that out. You can't cancel the numbers, but the variable x will cancel out in every thing in that statement, and you only have one unknown to solve for, and it's an easy rearrangement. But is it going to be plus or negative? That's the question. So let me work this out. 8 times 12 minus 3 times 30, that's minus 90 divided by 5. So the final answer is 1.2 meters per second, and the sign on it is positive. So there, interesting. Even though the bomb explodes and the two pieces of the train separate, the bigger mass, although it gets further and further and further away from the smaller mass, it rolls forward. That explosion wasn't big enough to actually push the big part of the train backwards, but it was enough to slow it down. And that's it. I would convert that into a final answer because they want specifically a direction statement. You always have to say, like, don't leave it as a sign, because signs are, there's no exact way to do the signs. You can make left positive if you really wanted to. So people won't understand your interpretation of signs until you have a final answer in square brackets. In this case, forward. Okay, so there are 4 practice questions for today. They're exactly like these examples. They're quick. You set the situation up and solve for the only unknown. The answers are all provided on the page, so you can check them pretty easy. The only one that gave people problems last year, and there was no reason for it, but it was number 2, because it's an archer and an arrow. And in the beginning, they're one mass. The archer is actually holding the arrow. So consider it one mass in the beginning, and then the arrow fires forward and the archer repels backwards. But in the beginning, there's 0 speed. So what an interesting kind of statement for that one. Let me write it off to the side here. You'll have something like this. A total mass in the beginning is going to split into 2, and the speed involved in the total mass in the beginning is 0. So the entire left-hand side becomes 0. Weird. And you have to work out whatever it's being asked for. And finally, in the end, I put one more question on here just to show you where you're headed. This is first year physics at Brock University next September, their online assignment for Momentum. You can try this question if you want. You'll see that it is exactly the same as the work we're doing. The only difference here is there's two differences. They would want an answer in kilometers an hour, so you have to remember to convert it in the end. And the other difference is, you see how these numbers here are a little bit bigger than the rest of the text in the sentence? That's because those numbers primarily generate for everybody's login. So you'll log in, the person beside you will log in, you'll want to do your assignments together, and all those numbers will be different for them compared to you. So try these questions out. Even though the answers are on these page, I'll post full solutions that we can take up tomorrow. And you're well on your way to, let's see, what unit are we on now? 1, 2, 3. You're well on your way into the third unit with a fourth unit to go.